We're super happy to kick this thing off. I'll be here this morning, and we're going to start things with Kenny Rogers, who's going to take a deep look at Stacks block production under the upcoming Nakamoto upgrade. So he's going to go deep on, how Stacks achieves finality with fast block production and what you guys can do to build in the Stacks ecosystem. So please welcome to the stage Kenny Rogers. He's going to take it away for our first workshop of the day. Let's hear it for him. Come on up. Welcome, Dad.
Thanks. All right, morning. So as Zach talked about, I'm going to dig into a little bit how Stacks actually works. And what I want to do today is basically just kind of go through what's actually happening under the hood in Stacks block production. I found that a lot of people kind of get Stacks at a high level conceptually, but not a lot of people really understand what's actually happening under the hood and what all those terms mean. So that's what we're going to talk about today. Quick little caveat, as Zach alluded to, this is how Stacks is going to work after Nakamoto's activated in August. So this functionality you won't find yet on mainnet, but you will find it on mainnet in August. And that's what we're going to dig into today. Real quick intro to me. My name's Kenny. I'm the developer advocate at the Stacks Foundation. So I do a lot of developer education. I work on the docs, do tutorials, workshops, events like this. Basically anything to try to help make developers as successful as they can be, building on the Stacks chain is kind of my role. And so what I want to start with today is just a real quick overview of what Stacks actually is. And the elevator pitch that I like to give is that Stacks is a Bitcoin L2 to activate the Bitcoin economy. So what do we mean when we talk about activating the Bitcoin economy? A book that I like to reference when I talk about this is Layered Money by Nick Bhatia, and it's not actually a technical blockchain book, it's more of a financial book. But what he talks about in it, what's happening here? There we go. What he talks about in it is that there's different layers to money. And so you have this base layer money. In the traditional financial system, you might think of like Fedwire as this system. It's a system that a lot of banks and institutions use to transfer large sums of money back and forth between each other. But we as top-level users, we never interact with that. We're behind all these layers of abstractions because that base layer money is difficult to use. And so if you bring that analogy into the Bitcoin world, we can kind of think of Bitcoin as that base level money that is as secure and immutable as possible. It's has that closed supply loop. And so what we want to do as L2 builders is we want to try and build abstractions on top of that make it as easy to use as possible. And so that's really what I envision Stacks doing, is it's taking that base layer of Bitcoin, taking that base money, and it's adding abstraction layers on top of it to increase the scalability and increase the functionality so that we can then build a financial system on top of it that's ideally as decentralized as the money itself, or at least as close as we can get to that. So this term L2 is a little bit of a hot topic in the Bitcoin world right now, and so I want to start by just giving a few properties of what I think makes a Bitcoin L2. The first one is that it inherits the security of the L1. So when I submit a Stacks transaction, when I submit a transaction on that L2, once it settles back down to the L1, it should be as hard to reverse that transaction as it is to reverse it as if it happened on the L1. So that's the first property, is that it needs to inherit that security. The second is that you can use the L1 asset as a medium of exchange. So we should be able to take our Bitcoin and securely and in a trust minimized way, bridge it over to Stacks, use it, and then bridge it back to Bitcoin. And then third, it needs to enhance the scalability or functionality, or ideally both, of the L1. If it doesn't do one or both of these things, there's not really any point in it existing at all, in my opinion. And ideally, it should do all these things while being a decentralized open network. If we can accomplish these things, but we have to do it in a closed system, that doesn't really solve the problem because we still have this layer of additional trust that we have to deal with when we're moving our assets in and out of that L2. So the way that Stacks accomplishes this is it has several components. The first is proof of transfer, and this is the block production mechanism. This is going to be the bulk of what I'm going to spend my time talking about today. The other two main components are clarity. This is the smart contract language. An excellent developer in the ecosystem, Jesus, is going to be talking about clarity quite a bit tomorrow. I believe that one's actually on the main stage, so definitely check that one out. And the third main component is SBTC. And this is that trust minimized two-way peg. So this is how we're going to accomplish that second property of being able to use the L1 asset on Stacks. And I believe right after mine on this stage, Andre and a developer from Trust Machines are going to be giving an overview of how SBTC actually works. So definitely check that one out to understand what's actually happening with SBTC. And what I want to do today is I want to show you how Stacks works, and then you can decide its viability as a Bitcoin L2. We're just going to dig into exactly what's happening under the hood, and then hopefully you can go away with a better understanding and decide for yourself, do I like the way this operates as a Bitcoin L2? So we're going to start with creating a Stacks block. And step one in this process is that a miner needs to spend Bitcoin. So the way that I like to describe proof of transfer is it's kind of one level up, again going with this layer analogy, one level up from proof of work. So if we look at Bitcoin, the way that proof of work operates is a Bitcoin miner will take one external asset, in this case that's raw energy. They will spend that for a chance to create a new asset, which in this case is Bitcoin. Stacks operates very similarly, and that a Stacks miner will take one external asset, which in this case is Bitcoin. They will spend that for a chance to earn a new asset, which in this case is Stacks. So what proof of transfer really seeks to do is recreate the proof of work in a programmatic way. So what a Stacks miner will do, represented by this little computer right here, is they're going to send BTC to reward addresses. And these reward addresses are generated automatically by the protocol using a random function. And so me as a Stacks miner, what I'm going to do when I run my mining software is I need to have Bitcoin attached to the address that I'm running my mining software with. And my mining software will then spend that Bitcoin by sending it to these reward addresses. And this is the first step in proof of transfer. So that where that Bitcoin is actually going, these reward addresses that are generated automatically by the protocol, they're generated by what's called a verifiable random function. And so a new set of these reward addresses are generated every roughly 2 weeks, which corresponds to a reward cycle in the Stacks world. And what I'm doing as a miner is I'm sending my Bitcoin to one of those 2 reward addresses per that Bitcoin block. So 2 of those reward addresses exist for every Bitcoin block. Me as a miner, I'm going to send that Bitcoin to one of those reward addresses. That's going to put me into that verifiable weighted random function, which means that the more Bitcoin I spend, the more likely I am to be chosen as the next Stacks miner. It doesn't guarantee it, so it's not like if I spend the most Bitcoin, I get to mine every single time, but it weights it based on how much that I spend. And it's important to know that if I don't get selected as the miner, I don't get that Bitcoin back, because the point here, just like Bitcoin mining, we want it to be that you have to spend an external resource, and we want miners to be economically competitive, and that they have to find that balance between how much Bitcoin do I need to spend to make it profitable based on the chance that I'm going to earn Stacks in this mining block. And who owns these reward addresses, where that Bitcoin actually gets sent, is it gets sent to stackers, and these are the other main party in the block production mechanism. So we have miners and stackers. And stackers really have 3 primary roles. One is they receive that Bitcoin that miners spend, but they only receive that Bitcoin if they fulfill their second 2 duties, which are to validate blocks proposed by the miners and then validate SBTC deposit and withdrawal transactions. And we're going to get into these a little bit in the next steps. So, step 1, miners are going to send that Bitcoin. Assuming that miner is selected by that weighted random function to be the next miner, then they're going to begin their tenure. So at this point, they begin their miner tenure, and this is where they're responsible for creating and proposing new blocks by including transactions from the mempool. Note that they're only responsible for proposing the new blocks, and we'll get into the second half of that in a second. But there's a lot going on when a new miner begins their tenure, so we're going to spend a little bit of time on this diagram right here. And we're going to look at this from the perspective of miner B over there on the right side. So me, as Stacks miner B, what I'm going to do to initiate my tenure is I'm going to submit a block commit transaction to the Bitcoin chain. So that's going to be a Bitcoin transaction. And that's going to include, one, the Bitcoin itself that I need to send to the reward addresses, but it's going to include a couple special encodings that will indicate to the stackers that this is my block commit transaction and indicate to the protocol. One of those things is that as miner B, I am going to include the first Stacks block that miner A mined in my block commit transaction. And we'll get into this more in a second, but this is one of the key parts that allows Stacks to achieve that Bitcoin finality, where those transactions are as secure as they're on the Bitcoin chain. This is what's actually going to anchor the Stacks tenure to the Bitcoin blocks themselves, combined with one other feature, which we'll talk about in a second. But once I submit that block commit transaction, if I'm chosen to be the miner by the protocol, then the stackers will then pick up on that, and what they're going to do in response is they're going to create what's called a tenure change transaction on the stack side of things. And this tenure change transaction is going to include a couple key pieces. One, it's going to include the current Bitcoin block that corresponds to my tenure. So in this case, that Bitcoin block B. The stackers are going to include that in the tenure change transaction. And the other thing that's a key part of how this works is that the stackers are also going to include the last mined block on the stack side. And then the stackers are going to send me as the miner that transaction, and it is my job to make that the first transaction that I include in my tenure. If I don't, then my transaction is considered invalid and the stackers are going to reject it. So that's how we avoid stacks forking. This is why under Nakamoto, stacks cannot fork. And that combined with that anchoring to the Bitcoin chain that we talked about is how stacks is going to achieve that Bitcoin finality. We'll dig into that in a little bit more detail in just a minute. But that's how this whole tenure change transaction works. And remember that this is initiated by the stackers on the stacks chain and then sent to the miners, and then the miners will then include that transaction as the first in the first block that they mine. And it contains the immediate parent stacks block and the current Bitcoin block. So then after this, once they have included that tenure change transaction, the miners are going to start proposing new blocks from the mempool. And then the stackers are going to append those blocks. And this is how that process works. This is the key role that the stackers play in the ecosystem. So we've got the miner here represented by the computer, stackers represented by that little data stack icon. What's going to happen is miners are going to send new stacks blocks to the stackers, and they are going to check and see whether it's valid based on the protocol rules. And if it is, they're going to append it to the chain, and if it's not, they're going to reject it. And there needs to be a 70% quorum, so 70% of the stackers have to agree on the validity of a block for it to be included in the chain. And then step 5 is we're just going to rinse and repeat this process over and over, and that's kind of the big picture of how the block production mechanism works. So I want to dig into a little bit more about Bitcoin finality. And in this diagram that we looked at, the Bitcoin finality happens right about there. So it happens at that tenure change. And what's actually happening right here is after miner B switches over their tenure to miner C, any transaction that happened during miner A's tenure is going to be considered Bitcoin final. So it's 2 tenures after where the transaction was included. And the reason is because remember that miner B, when they initiate that tenure change transaction over to miner C, they have to include the first transaction mined in miner A's tenure. And so we have this n+1 system for whenever a stacks miner submits their block commit transaction, they're including the previous miner's first mined block. And that is what's going to anchor, and remember, that's on the Bitcoin chain, so that's what's going to anchor that history to Bitcoin. And so this, plus the fact that stacks cannot fork on its own, it means that me as a stacks miner, even if I were to be able to control the majority of the funds on the network and conduct a stacks version of a 51% attack, I would not be able to create my own fork of the stacks chain and conduct a double spend because those transactions are anchored to the Bitcoin chain. And on the stack side, we're able to read that connection and read the last mined stacks blocks, and basically the stackers will then mark that as invalid because that would actually be an invalid transaction according to protocol rules. So when a miner is mining during their tenure, they're going to be producing blocks on the order of seconds. I think the last benchmarks I saw were about 10 seconds. So they're going to be continuously pushing blocks to the stackers, and the stackers are going to be appending them. And then we have this Bitcoin finality here. And that's how stacks can get these fast blocks and get this Bitcoin finality under Nakamoto. So we kind of looked at all that in pieces, and this is sort of the big picture of how it all works. So we'll run through one quick recap. Stacks block production, we have 2 main parties, miners and the stackers. Step 1, miners are going to spend their Bitcoin. They're going to send it to one of those reward addresses. The stackers are going to pick up on that block commit transaction, which happens on the Bitcoin chain. They're then going to initiate that tenure change transaction, which is going to include the last mined stacks block. Then the miner B is going to include that tenure change transaction in their first mined block. Stackers are going to pick that up, append it, and then the miner will begin producing and proposing blocks from there. And then stackers will either approve and append it or reject it based on the validity of the protocol. So that's the big picture of how the block production mechanism in stacks works. I'm going to go over a couple more, touch on these a little bit, the other components of stacks. The first is clarity, and clarity is the smart contract language of stacks. There's a couple properties of clarity that are a little bit unique. And the 3 main ones that I found are that it's decidable, readable, and concise. And so when we talk about decidable, what does that mean? Decidable is similar to being non-Turing complete, and what it basically means is that there's no concept of unbounded loops in Clarity. So there's no for loops, there's no while loops, and what this does makes you have to think about how you write your smart contracts a little bit differently. But the benefit here is that you know exactly what a smart contract is going to do before you execute it, and you can actually see exactly how much it's going to cost before you execute it, because there's a finite number of execution paths. There's not a theoretically unlimited number of execution paths. So there's no concept of like running out of gas in Clarity, because you can tell before you initiate the transaction how much it's going to cost. You can plan ahead for that, so you're not going to run out of gas in the middle of a call. It's highly readable. So Clarity is a Lisp-based language, and so it's a little bit different than what you might be used to in Solidity. But you'll find that once you get into it a little bit, it's very readable and very concise. So one of the downsides of using an object-oriented language like Solidity is when you're inheriting classes and libraries from other projects, there's a lot of functionality kind of abstracted away from the actual contract code that you're writing. But in Clarity, literally everything that happens in your contract has to be written out line by line. So while this makes it a little bit more verbose to write your smart contracts, I think it makes it a lot more secure, because you can go through and you can check exactly what your contract is going to do right inside of the contract. If you have any other contract calls, it's just going to link you right to that contract to see what that's going to do. There's no abstracted away functionality behind other classes and other libraries. The other main component, again, that's going to be talked about in detail in the next talk is SBTC. And this is that trust minimized two-way Bitcoin peg. So this is how we're actually going to be able to use our Bitcoin on the Stacks L2. And crucially, this is an open network. So this is one of the biggest differences between SBTC and a lot of other two-way peg protocols, is that stackers are an active participant in this system for validating these SBTC transactions, and anybody can become a stacker. So this is one of the key differences, I think, and this is one of the things that I think is key for a two-way Bitcoin peg. If your two-way Bitcoin peg is controlled by a closed federated network of validators, that doesn't really solve the problem, because then you just are introducing an additional layer of trust there. With an open network, that layer of trust grows more and more decentralized over time, and that's really the goal with how we want to build this out. It's a one-to-one Bitcoin peg, so if I'm on the Bitcoin chain and I want to mint SBTC, I will deposit my Bitcoin into the peg wallet, and that will then automatically mint exactly that amount of SBTC on the stack side. Same thing when I withdraw, it'll burn that amount of SBTC and pull out the corresponding amount of Bitcoin into my wallet. And then the third thing is that SBTC operates as a SIP10 token. This is just the standard for fungible tokens that we use in Clarity. And the benefit of this for developers is that it's really, really easy to work with SBTC. Literally, all you have to do to actually work with it is just call the fungible token transfer function that's built into Clarity itself. And that's all you have to do. All of the complex stuff is going to be handled by the protocol and happening behind the scenes. And so all this summed up with this functionality is really to say that Stacks is trying to answer the question of how do we use Bitcoin in a new open, fair financial system, and do that in a trust minimized but scalable way. And these components, proof of transfer, Clarity, SBTC, are how Stacks comes together to try and actually accomplish that goal. So next step for you guys, for anybody that's interested in actually building on Stacks, these are the resources I would recommend. First one is the docs. Go here if you are brand new to Stacks and don't know what it is. This will give you the intro. This will give you a bunch of technical tutorials, walk you through Clarity, link you out to other resources. LearnWeb3.io is a really good guided sort of start to finish intro to Stacks. So another good place to go if you're brand new. Docs.hero.so. Hero is a major developer tool company within the Stacks ecosystem. So if you need to do anything with Stacks, you're going to be touching Hero tools. And so there's a great place to go to learn how to do that. And then if you're new to Bitcoin in general and not quite sure what building on Bitcoin actually looks like, the Bitcoin Primer is probably going to be the best place to go, and that's at bitcoinprimer.dev. The first half of that will give you an introduction to Bitcoin itself, and then the second half will give you an introduction to how to build on top of Bitcoin with Stacks. So that's it for me. Thank you, everybody, and just feel free to walk up to me if you have any questions, anything like that. Thanks.